Hello, everyone. Welcome to our third AI ML seminar being hosted out of NASA Ames through the exobiology branch by myself and Caleb Scharf. Today, I'm happy to be introducing Bethany Theiling from NASA Goddard. And was kind of serendipitous. I actually cited Bethany's work for my NPMP application that essentially got me to working with Caleb on this AI ML initiative where these seminars are one component of those. So it's very nice to have that come full circle and have Bethany here with us. She'll be discussing her work on applying AI ML to planetary science missions that essentially is a stepping stone from an earlier paper that was on the science autonomy and a perspective on this that she wrote back in 2022. And I believe she will reference that paper at some point here in the talk. But again, please keep your mics muted. If you have any questions, we'll take them at the end. And you also feel free to post them in the chat and I'll aggregate all of them. And with that said, Bethany, please take it away.
All right, thanks. First of all, and thank you so much for hosting all of these seminars. I've really enjoyed them so far. So yeah, keep going. I'm excited. Victoria already has a question. Apparently, we haven't even started. I'm just
so
joking.
sorry. I wanted to clap and not raise my hand.
That's okay. All right. Yeah, so thank you for the introduction. Thanks for the invitation. I am super excited to get to talk to you guys today about the work that my teams have been doing. So yeah, my name is Dr. Bethany Theiling. I am at NASA Goddard Space Flight Center in the Planetary Environments Laboratory. If you don't know what I typically work on, so I'm an ocean worlds geochemist, but I keep dabbling in other things. So I don't know what I want to be when I grow up still. I keep doing things on Mars. Now I'm doing things on AI. So I'm kind of all over the place. But all of this work has kind of come together really as this onboard AI framework. And I want to be just out of the gate. I wanted to describe to you guys like this is supposed to be a tool to help our science teams. So one of the first things that I get from people is like, is it going to take my job? The answer is no, it's not going to take your job. But we want to make sure that you can do the best science possible while we're out in the solar system. So I have a lot to talk about today, so I thought it would be good to just go over a little bit of an agenda. First, I'm going to talk about why we're doing this at all. So, what are the motivations? Then, I want to talk about what we're doing. So, what are the kinds of machine learning approaches that we're using? And I'll try to be more specific towards astrobiological detection. I'll talk a little bit about how we're actually integrating all of these efforts into developing this onboard AI. And I want to be very clear, it's specifically for science. So there's a lot of artificial intelligence development that's already going on that is specifically focused on things like, automatic targeting, for instance. So that's science-based, but it's based very much on a specific target. There's also things like and we've seen this with Perseverance, actually was able to find a place to land and then land autonomously. So there's these sorts of AI-esque frameworks that are already in development. The one that we're working on is specifically geared towards science based on science data and on board in real time. After that, I'll talk about the simulation. So I'm going to show you some animations of the simulations that we have. And it's basically how would this AI work in a simulated mission in Enceladus. I'll talk a little bit about the prototyping we're doing with various hardware, and I'll probably put a call out there. And if I don't, I'll put a call out there right now. If you are interested in using your hardware with this kind of thing, please come talk to me because we're really interested in partnerships. And then how can you use this in your mission, and what are we doing from here? So to jump right in, Caleb gave a great introduction. So what are the motivations for this? I've got a QR code here. So this is the science autonomy for astrobiology, I think, a perspective. So this is a piece that we got in astrobiology a couple years ago. I think it was finally published in 2022. We did an earlier white paper in 2020 for the astrobiology and planetary science decadal survey. So that was a follow-on from that. And really, it talks about, for ocean world specifically, what are the kinds of things that we're going to need? We put it out there as a kind of a community service. Like, we know that there are these needs that exist, at that time, if I could write that paper over again right now, I could tell you it would be a dramatically different paper because we've learned so much in such a short period of time, which is, again, why Ryan and Caleb, I'm so glad that you all are doing this. It's just great to have this community resource out there. Okay, so there's a few challenges, and I'm going to do this as quickly as I possibly can because there are so many. I could give an hour-long talk just on the communication or just on the challenges that we have for doing astrobiology. So some of them are just based on communication. So if we look at the solar system, and here's you, and I think everyone's coming from Earth today. And I'm going to pick on a few of these outer solar system targets. So if we're just thinking about the speed of light, it's about 35 minutes to send a signal to Jupiter, and then it gets longer and longer. So 1.2 hours to Saturn, 2.5 to Uranus, and so on. So it gets much more challenging. However, what we have to add, so the complicating factor to that is that you now have to think about your spacecraft in position to Earth, because right now we're sending all of our data and communications back to Earth. And so this can get really challenging because if we think just about the Jupiter system, and I'm kind of picking on Europa, but it's my favorite, so it's fine. So for the reports that I've seen it's about 8 hours, generally speaking, to get communication back from the Earth back to Europa during this flyby mission, so that's Europa Clipper. There might be some differences based on updated models. And then I've seen projections of upwards of 43 hours if there was the Europa lander. And so you can see how challenging this is. So basically, I started thinking early on, if we're for instance, if we're on the surface of one of these systems, especially an astrobiological target, we're just sitting there in a very extreme environment. And so is there something that we could do while we're there without having to talk to Earth? And that's what really got me thinking about this. And I have to give credit to people like Victoria Dapoyan, who I met very early in my time at Goddard, and also Eric Linus, who've been working on this for a longer time than I have, who really keyed me into this problem. Then if you start thinking about missions, like really exciting missions, like what if we could go underground? So what if we could get out of these really harsh radiation environments and go underground? Where, I love this EELS mission concept that was coming out of JPL. And so basically, once you start going underground, it gets even more challenging to communicate. You'd have to have some sort of relay system. So you really have to act autonomously. And in many cases, these mission operations have been meticulously crafted, but they leave no room for error and they leave no room for updating on the fly. And so here's another one. This is actually a recent test. I think it was last spring, 2023, where you have this basically repeller robot that's going through a skylight into a lava tube and then crawling around inside the lava tube. So it's a really cool concept, but a lot of them have really rigid ConOps. Now we get into data processing challenges, and you can see this image comes from Victoria Dapoyan. And the instrument that I most commonly work with is a mass spectrometer. I'll talk a little bit more actually a lot more about them later. But what I want you to see here is this projected astronomical increase in data volume. And so this is the launch year and the samples per second that's anticipated. So we have the Mars Science Laboratory, which is a quadrupole mass spectrometer. And you can see we've got its data volume appears very low on this particular scale. Once we start getting things like the ion trap mass spectrometer that is currently integrated onto ExoMars, that's the MoMA mass spectrometer, so increase in that. And then if we think about the potential for future orbit trap integration, those data products are massive. And so now we have this, not only do we have the higher resolution mass spectrometers causing problems, but even if we were to put in just projected like ion trap mass spec, what kinds of data volumes they are, the projection is that they would also exponentially increase over time. So we need a solution for dealing with this on board. And to get into that, I could also give an hour-long talk just on the theoretical challenges here. So this is going to be a little bit of a fire hose of information if you're new to this. But I want to bring up this idea of there are so many different ways to think about in the solar system or beyond. And so one of them, I'll bring up a few of them. This is mostly for people who are maybe new to this, or just as a reminder. This is the ladder of life detection that was by Mark Neveu et al. In 2018, and this is the updated version that was in the Enceladus Orbulander. And you can see, like, there's a lot of different things that you could look at. And then there's this question of what's the dead ringer, though? What is actually life? And then you get into questions of, well, is life on a different target going to be the same as life on Earth? So there's a lot of really exciting work that was done. And if you were to take this table and move it out, you could actually see what kinds of instruments they suggested, which it was a great paper, especially the Enceladus Orbulander report. There are also these great ideas about molecular complexity, chemometric fingerprinting. So these are just a few examples. And for some of these, if you were going to have to do them on board, they would be computationally expensive, and you would have to do them on board. So they're really challenging. And so if we were ever to try to implement this, you'd have to have a way to do that. Now there are things, and again, fire hose of information, but part of this in trying to identify a biosignature is, the challenge of the standards of evidence. I really liked this figure from that document. I encourage you to look at it if you have not. So how do you go from discovery to thinking about the where that could it be mimicked by biochemistry? What's the context of it? Are there independent lines of evidence? There's a lot of great resources coming out from the life detection knowledge base. And I think that there's supposed to be a volume of papers coming out, hopefully in the next few months. They're all about how you use that. And then there are things that are really like this, is it suggestive? So what is beyond reasonable doubt? What is within that reasonable doubt? And we're learning more every single year. And so how do we keep up with this? One of these papers that came out, I had the great pleasure of being a part of this particular authorship group, but it was this range of prebiotic chemistry and how that could change depending on the context that you're in. And so if we're thinking about all of these things and the pace at which our astrobiological science and origin of life science and prebiotic chemical science, the pace at which we're learning things, I think AI has the perfect opportunity to keep up with those things. And so really what I'm trying to get at here is that AI can enable all sorts of things. So we could be able to see and identify novel events. So maybe, and I love this image because I want to see it one day. I want to be able to know that we detected cryotectonism or volcanism on, for instance, Europa or Enceladus. I think that would be incredible. But I also think about, like, what if we could respond to that in real time? What if we didn't have to wait months or years or miss an opportunity to take, new images or get new mass spectra or something else? So really, could we react to those observations of interest? And I'm just bringing up this projected plume detection that was kind of the earliest one. I think it was Roth et al. 2014. It's right behind my camera, so I can't see the dates here. But this was the oxygen detection. No, it's the hydrogen detection. I'm trying to remember. and this was the earlier one, but these were presumed plumes, but we don't actually have confirmation of that. And there's been kind of a back and forth for years about whether or not that was confirmed. And I'm on the side that I think it's actually plumes, but I don't think they're very big at all. So it's going to be really hard to respond to them, and I think that we'll have to do it in real time. And then reacting to potential biosignatures. So, this is, I put this like very basic, AI generated spectra up here because it is going to take a lot for the community to be able to accept a potential detection. And I think that if we were able to respond to that in real time, then we'd have the opportunity to the opportunistic science, I make this joke a lot, but it's sometimes we don't know what we don't know until we realize that we don't know it. And so we might be out there where every single spaceflight mission, we learn something that we didn't even expect to learn. And so I think that AI could really help us respond to all of these things in real time. Okay, so how is my group doing this? There's a lot of different approaches, and it's going to be very, very quick, but I'm trying to get through it so that you all can see how we put it together and then hopefully have a lot of time for questions. So I brought up mass spectrometry before, but just so that it's out there, what is a mass spectrometer? This is a magnetic sector mass spectrometer. So your sample enters over here. Excuse me. It is ionized, and then those ions are accelerated, and the beam is focused. This is not the perfect diagram, but the ions are accelerated and you get a focused beam. It interacts with a magnet. And you have this magnetic field here, and then that magnet will bend the ion beam such that it separates each of these charged particles by mass. And so you'll end up deflecting particles that are heavy mass a lot, the lighter ones a lot, and then heavy ions not as much. And so our detector's calibrated to measure those sorts of things. And I think while I was talking, these were playing, but let's just go ahead and start those over again. Hopefully they'll play. There we go. So I've got just two examples here where you've got these two different kinds of spectra, and this has been proposed by some as being like, okay, well, let's look at these two different kinds of molecules or multiple kinds, map them out. This is a really easy task for a classifier to say, well, these are super different looking spectra. You guys can tell the difference, I think. So you have mass overcharge on the x-axis, and this is actually intensity on the y-axis here. So this is pretty easy, right? Now, we could use something like this, or we could have used something like this on the Cassini mission. We did not have the technology at the time, or really the knowledge that this would be something we could use it for. So I'm not saying anything bad about Cassini. It did an incredible job. It was awesome. But I keep thinking about what if we could have had this at that time? And so let's deploy it on the next mission. So there was, just to make sure everyone's on the same page, we had, carbon dioxide, methane, silica particles, all have been detected in Enceladus's plumes. And this paper that came out in 2017 detected hydrogen. And this is a really exciting detection for many reasons. One of which was that now we have models that suggest that there's enough chemical energy to support methanogens, which is incredibly exciting. So it can support life. We're above we're in the disequilibria. We're not at equilibrium with it, which is death. So, and what you're seeing, if you've not looked at this figure before, so this is the background down here in the kind of the greenish color, and then light blue is a 1 sigma detection. The dark blue is a 2 sigma detection, and then this kind of purple violet is the 3 sigma detection. So one of the things I thought would be really easy, and this is not machine learning, this is just a threshold detection, to say, what if we were able to code in that anything above, and I'm just randomly selecting 2 sigma of our background, that is something important enough to tell me immediately about. And so maybe that's something that could be used to help clue our science teams into, hey, go look at this data. This was really exciting. And maybe it's anomalous. Maybe the instrument did something weird. I don't know. But it could actually be an easy approach for that. So all of this, just because I put this beautiful picture of Lost City over here, all of this suggested that it's very similar to Lost City, which is an alkaline hydrothermal vent. Okay, so up until now, I've presented this as like, it's so easy. Everyone could do this. I loved this paper that came out fairly recently. I think this was like last fall. I want to say it was like last fall or last summer. And so they were looking at more complex data. So these solutions, like our own seawater, are salty. And so if you were to look at just sodium chloride, and again, we have the M over Z, or mass over charge, and then the intensity of that, these start to get really complicated. So the mass spectra gets very, very complicated very quickly. And I work with salt. I don't like organics. I think they're gross and they make everything weird. So, but it does make things complicated. So now we get into organics, and this is from the same paper, and it makes your spectra incredibly complicated. So this is where you can start thinking about, like, could I train something to recognize the differences between just a sodium chloride solution and something that actually had organics in it? So this is one of those things that I thought was really compelling early on. So I'm going to break down that spectra for you all, because I think it's important for the next couple of slides that I'm going to show you. So one of the things is just your limit of detection. So we think about, okay, when do I want to make this important? How do I say that this is important? And it could be depending on your mission. So maybe your mission is, hey, if you see anything that is above the limit of quantification, please alert me. That would be a nice thing to do. Maybe you have the computational power for that. Maybe you have the bandwidth for that. Or maybe you're like, hey, you know what? I'll get to the data eventually, which is kind of the way that we have been working with data. Or you could say, I need a bit of a higher importance put on that. So maybe it's like based on some sort of a priori model. There's like, if this kind of chemistry is happening, this is what I think my spectra will look like. It could be based on onboard learning. So it's like I go out there with an assumption, but then I start to learn what my environment looks like. And so I say, oh, it always kind of looks like this. So I'm not going to start sending that home anymore because this is just kind of what Enceladus looks like, or Titan looks like, or Europa looks like, or what have you. So you can decide where to set that threshold. I've used this word a little bit already. Or you could say, I want this to be something I don't expect. So maybe as you go through your mission, you're starting to see things that are outside the norm. And that could be, it's just a really massive detection. Or it could be, I've never seen this before. So you can decide, and this is the thought process that we've been taking of how we would build an onboard AI framework. Now, just to be really clear, we were using laboratory experiment data to do a lot of our initial training for these models. And I'll talk a little bit more about the kinds of new models we're developing. I just wanted to put the plug out here, shameless self-promotion. But I published a lot of the work on the early abiotic samples in Icarus in 2021. Victoria ended up, she published on EDA, so that's the exploratory data analysis techniques. I'm going to talk a lot about that in the next few slides. So I encourage you to go read those papers. And then we've got a few more papers. Lily Clough, who's my grad student, she is like this close to submitting an awesome paper. I'm so excited. So, keep your eyes peeled for that. And I've got another one that's in prep right now, actually two. So the samples that we worked with was effectively their rock-water interactions, and this is just the hypothesized scenario that we're working with. So we know that there's rock-water interactions. You can presume from that that CO2 would be created. This is not something that I think is controversial. They would interact with that seawater and ice, and then we will measure that CO2 using, in my case, a mass spectrometer during a flyby mission or an orbiter mission or what have you. And so in this scenario, we had different kinds of seawater solutions, different amounts of CO2, different amounts of microbes or no microbes. And so that's the data that we used for all of our modeling. Now, the spectra that we used are from a commercial isotope ratio mass spectrometer. So they are different. We are right now starting to do the work of getting that translated into more of a flight-like mass spectrometer. So I do have to, state that caveat just up front. So now in this case, we have time on the x-axis, intensity on the y-axis, and we are looking at a specific kind of gas. So instead of saying, what is a bunch of different kinds of molecules that I might, ionized particles that I might see from a larger sample, I'm looking at just a particular kind of gas, and I'm looking at isotopologues of those gases. So just to give you a sense of what we do, this is the reference gases are these rectangular peaks. These are things that we use to calculate what the isotope ratio is. These are our sample peaks over here. And I think I actually have a little box. Yep. So we actually use these for fear that this particular one could be contaminated from a previous sample. And this is us trying to remove any potential contamination. So these are the ones that we train off of. Okay, here's where things get crazy. So don't panic. I know there's a lot to see in these figures. So if I go back here, the output from this from the software is going to give us 41 features. That means, in layman's terms, 41 columns worth of information. And so if we say all 41 features are over here, so we did a cross-correlation matrix to say, but how many of those things that the program outputs is effectively the exact same thing? And so things that are exactly the same are in green. So basically it's like some are no-brainers. So if let's see, these are barely readable and I apologize. Peak number to peak number. So if we plot peak number and peak number together, they're going to be exact. The peak number over peak number is 1. It's the exact same thing. Okay. So if you go, any of the greens are pretty much the exact same thing. And so we decided to reduce those numbers because we don't need to bias our model by adding effectively the same information into the model. So this is a way to do what's called feature selection. The red is things that are pretty interesting. So they don't seem to be repeated. And so this is a way for us to use the data to drive feature selection. And there are lots of other ways to do that. So we're not done here. Another thing that we can do, so this is actually showing you a principal component analysis, which we've seen in other kinds of papers. This is a pretty common statistical technique. And so in these particular figures, I know, again, this is a lot to look at, so bear with me. Each color of data point, and I think that there are, I can't remember exactly how many colors there are. I want to say that there's like 36 or something. That is a specific seawater composition. So we had a lot of different kinds of combinations of seawater because we don't know exactly what we're going to be looking at. And so what you can see is that if we use more features, and what I want you to get out of this is that more features tends to be a little bit more difficult to interpret. So we don't really know what, and in a PCA, you're trying to figure out what are the important parts of that data that are creating this feature space. And so if you decrease them, you can see like, oh, okay, the blue ones, which are actually magnesium sulfate solutions, they tend to be kind of clustered more closely together. And these orange ones tend to be clustered more closely together. If you were able to zoom in a little bit, and I can see it because I've looked at this before, but the isotope ratio, so the carbon isotopes are actually being projected on this PC2 pretty well. So if we then go down into 2 features, we might be losing information, but this gave us that understanding of okay, I think feature selection is going to be really important. And a plug for this paper, so please go take a look at it. Victoria talks about, or we all talk about the methodology for how you might go through a complicated data set and the steps that you might take. Now I'm going to show you some TISNE and UMAP. They are dimensionality reduction techniques. And the reason I'm going to pause here for a moment is because, again, think about that Excel spreadsheet or what have you, or your CSV file. You have many different columns. And so in this case, we are doing a 2D projection of a high dimensional space. And so here's your high dimensional data point. It's in 2 dimensions. And effectively what that means is that if you were to rotate this on its side, it would be the combination of all of these different things. And there's many more. This is just some that I put on there. So it's like the isotope ratio, the intensity, the peak area, the retention time, other kinds of metadata maybe that you thought was important depending on your data set. So now when we look at that, and this is pretty complicated, but basically everything that you see on here in green is biotic, everything in gold is abiotic. So this was an early way of us looking at this and saying, between PCA or TISNE or UMAP, are there ways to make it easier for us to identify biotic versus abiotic? And it seemed like PCA was probably not the way to go. And so what we were hoping is that we could have this easy, and if you've seen me give earlier talks a few years ago, you might remember that I was like, we're going to create a map of this where you could plot your data. It's not that easy, unfortunately. I wish that it was. But these did give us a really good understanding of the structure of the data that then enabled us to start working on some machine learning modeling. So basically, what I want you to get out of this is that PCA was not quite as good a technique as maybe TISNE at determining biotic versus abiotic, and that was maybe not as good as UMAP. Now, what was not demonstrated on these plots at all is that there's variable chemistry. And so we have a lot of other work to do. And I know Victoria and myself and Lily, we've all got various papers in prep where now you can see how all of those get pulled out into separate classifications. Now, what was very accurate, sorry, lost my train of thought there. So it was very, very accurate for us to use random forest. And we used combinations of supervised and unsupervised random forest models. So the talk last month, really great job, guys. That was awesome. I enjoyed it. They talked a lot about random forest. I'm not going to spend a ton of time going through it, but have a look through this again. So basically, you're sending a sample in. It is coming up with a decision tree for how to say kind of true false of is it this like this or is it like this? And it'll go through that decision tree, come up with a result like I think this is biotic. I think this is a magnesium chloride solution with biology in it. And then you'll see multiple trees, and then they have to kind of average or have a majority vote on that. So this is super early results coming from Lily Clough's paper that is, like I said, this close to being submitted for publication. Very good, really, really cool stuff. So she was using a nearest neighbor projected distance regression, so NPDR, and with a lasso penalized unsupervised random forest. It's a lot. These acronyms get to be a lot. I know. And so if you're not used to looking at these classification tables or confusion matrices, then basically what they're saying is, if you have an abiotic sample, how many of those were classified as correctly as abiotic or incorrectly as biotic? And so that's kind of how to read these tables. And so the accuracy is the most important part for, I think, the layperson or the person trying to read this very quickly. And you can see that they're very, very accurate. We did this in multiple ways, and this is just a few of the different kinds of models that we used because we really wanted to see, like, what kind of feature selection should we do, and what kind of models should we use. And I want to steal her thunder, so please, keep an eye out for that paper because it's really exciting results, and she does an incredible job detailing how we came up with this. Another thing that's going to come out in that paper that I'm really excited about is the interpretability. And there's another one where she goes through the false positive, false negative, true positive, true negative. These are done in various statistical ways. So I think that one of the exciting parts of that paper is how to now take something like this and turn it into something that we can all trust. That's not just about the accuracy. Like, how can we use these models and how do we trust them? And so one of them was this regression-based association interaction network, or RAIN. And what we did is basically plotted in this space, how do each of the features of the spectra relate to each other? And we thought about them not only as what we call MS, or mass spectral features, like the isotope log ratio, for instance, but also in the TS, or time series. So how does the timing of seeing that peak detection matter in terms of understanding whether it's abiotic or biotic? And so the green's biotic and the gray is saying it's more on the abiotic scale. And this is the kind of information I'm happy to talk through questions later on about how you could use this with a spaceflight mass spectrometer. And we've got some really great ideas about that. Okay. I know that was a lot. So let's all take a deep breath. What I'm going to show you now, because we have had years now of like, how do we develop these machine learning algorithms? How do we understand the data? How do we use it? And then, because I'm never satisfied, I'm sorry. If you worked with me, I'm so sorry. I love you guys. But how do we then take all of that information and then actually integrate it on board? And so this is kind of the data analysis feed through that we're kind of thinking of. So effectively, you've got your input data, and it could be whatever kind of data you're using if you're out there and interested in this kind of thing. We do various levels of statistical analysis. There's also some QA, QC processing. So it might be looking for anomalies that are based on either good or bad data, like data quality, or it could be anomalies for science. So that's part of that statistical analysis. Then if you wanted to, so you could shunt all the way around here and just go to recommended action. So it could be like, hey, anomaly detection, that's what I want to use this step for. And I want to prioritize transmission, or set, like, can I do another kind of analysis, or ask another instrument to do an analysis? So that could be your action. Or you could say, I want something more complicated because my data is more complicated. And so we use multiple machine learning models. That's why you see all these different kinds of clip arts here. We feed all of them into a central framework, and then that pops out a recommended action. So it will analyze that data and then have a recommended action. And of course, a greater agent in that framework has to say, I approve or reject. All right, so the way that I'm going to show you how this works is through a simulated small sat constellation mission at Enceladus. And so what you're seeing here is Enceladus sort of rotated up at you so that you can see the South Pole. The reason we wanted to show you this is because these particular orbits cannot pass directly over the South Pole, which as a scientist, I was pretty bummed by. But, you know, my orbital dynamics team basically said, I cannot do that and then not have it crash into Enceladus. And I said, well, that's unacceptable. So here's our compromise, is having 8 small sats. And what you can see is that at least they can get some sort of coverage of the South Pole. So those big cones are their maximum rotation and how they could at least observe the South Polar region. And this is not new. It's not a new model, but it is the first stable constellation model, which is really exciting, and I'm so proud of them for that. We also modeled the communication pathways. So basically, you have to see which of these small sats can communicate with each other and when, because we want to be able to simulate this accurately and say, okay, well, if one of these spacecraft sees something interesting, can it even communicate that to the correct spacecraft at the correct time? I know nobody wants to see code run in real time. Well, maybe some of us do. I know I'm excited about it, but I did want to show you this console. So basically, this is not code. This is a console that can show you what is being done. So we're using Redis, a console called Redis to show you that. So basically, I have 3 columns here, and there are 3 consoles or three terminals. So you have spacecraft 2, spacecraft 1, and then in this particular case, we had a mothership that was basically acting as an arbiter. So it was saying, okay, you send me what you want, and I will make the decision. And so what's going to happen in the demo that you're about to see is, and you're actually seeing a little bit of it right now, is that it will actually analyze the data, and then it'll pop up this thumbnail and then come up with an analysis. So you're going to see that in the full scale demo. All right, so I'm going to start this. What you are going to see is now we have a map view of Enceladus. So we flattened out Enceladus into a rectangle, and you're going to see all of the ground tracks of each of these spacecraft. So it's where on the ground they are hovering over. Because we can't go over the South Pole directly, we're interested in this tectonic area that I've got in a white circle right here. You can see spacecraft 2 is approaching this really interesting area right here. And so what we've done is taken some data that we've randomly selected from our cache of data and just thrown it into this model to see what would happen if this was happening. So what you can see is, you know, we've done all the timings are correct. It's actually doing the analysis in real time. It's actually doing it faster than it would need to do it on the ground, or sorry, would need to be able to do it. You can also see, if you are looking really close at this, it says loading machine learning models and QC algorithms. So it actually pops up, what do I think that this is? It's a magnesium sulfate seawater. What's my confidence that it's a biosignature? 72.5%. So it comes up with a decision, and then it sends that decision to the mothership and requests action. So the mothership, in this case, has to be the arbiter to say, is any spaceship nearby? Spacecraft 1 is. That's this one right here. And so it's going to repoint at this particular area so that it can try to open its gate, the gate to its mass spectrometer, in enough time to try to get some analysis. So that's kind of how this is going. So you can see performing slew for novel detection of confirmation. It's starting to do its performance. It comes up with an analysis. You see the thumbnail of that. It also starts loading models. And so it's doing all of this analysis on board in real time. It'll pop up with an analysis here in a few seconds, I think. Take a moment. There we go. It's very, very fast. So it has 79.6% confidence that it's a biosignature, and its decision prioritized transmission. So hopefully what you can see here is the interplay between multiple agents, and it could be multiple spacecraft. It could be multiple instruments on one spacecraft. It could be a probe and an orbiter. So there's a lot of different things that we could work with. And right here, I just wanted to throw this up here just for that particular demo. There was a ton of different groups doing a lot of different work, and none of them were planned. We all just happened to be working on the same sorts of things and serendipitously got together. So it's been great. I know I've got a little bit of time left, and so I wanted to talk about very, very briefly, like 5-ish minutes, about the kinds of prototyping we're doing. So here's my summer intern. So I have Leighton McKinney is up here. Where did my cursor go? There we go. So this is Leighton McKinney, and this is Connor Williams, and this is my grad student. This is Lily Clough, and they are out at the Great Salt Plains in Oklahoma this summer. So they built these sensor arrays. So this is they built the box. They built a touchscreen with an app attached to it, so it can actually be an AI-assisted human exploration. So this is kind of their summer project, and I'm incredibly proud of all the work that they've done. So what they did is train some a priori models using curated specimens. So basically, they went to the geology department at the University of Tulsa, took a lot of rocks that we thought were characteristic of maybe an environment that they could go to, and they started with a very, very cheap sensors. They started training machine learning models. And so these are, you can see that this is on a paint stick. I love it. It's amazing that they put all this on a paint stick. They created their own box. So the UV vis near IR spectrometer is actually in the hole right there. It was getting blasted out with light, and so they created this little cover for it so that they could use it out in the field. These are just Adafruit sensors, so they're less than, for the most part, less than $10. I think the most expensive sensor I bought was like $30. So this is a really cheap way of trying to do these like updated algorithms and prototyping on the fly. They were able to do some anomaly detections in the field, which is really cool. So they used this. They wanted to simulate if they were astronauts in a place that was very Mars-like. So this is a gypsum evaporite lake. And so this is very similar to places that Curiosity has been. Actually, I think it was like last summer, Curiosity started going into these sulfate deposits. And then here's just a projection of what some of their models look like. So here's the spectra that they're taking, and then it's actually coming up with a random forest prediction with a probability here. And so it's what is the probability of this particular class they're seeing? And so this is just an example of some of the data and the kinds of things that they're seeing. Some of the most recent work, so they're now taking those little sensor arrays and they're integrating them onto turtlebots. And so here's an example of one of our turtlebots. You can see it's got the contraption that has our UV vis near IR little spectrometer on there, like chip spectrometer. It's looking at some sulfur. I know this is very contrived, but these are the tests that have to be done, right? And so we were very happy to see that they're using these machine learning classifications, and the turtlebot now has to prioritize its position and continued exploration based on the classifications. So what you can see here is that, again, we're using random forest. It works great for a lot of this work that we're seeing. So very simple, sulfur versus non-sulfur. And you can see, oh, yay, sulfur. It's looking directly at sulfur. I think we can all on the line see that it's sulfur. We were very excited when the results came out recently of Perseverance seeing sulfur deposits on Mars. So that was extremely exciting because we're like, hey, we have the ML algorithms to help you with that if you wanted it. All right, ongoing plans. I told you that was going to be really, really quick, mostly because that's just getting wrapped up right now, and we still kind of have to do a debrief on all the things that they've done. All right, how are you going to do this on your mission? So we're trying to think about building all of this AI framework as an entire ecosystem. However, we're also trying to build it so that it is modular, so that you could say, you know what, for my particular mission, I want the science agent. So this one up at the top, the intelligent sensing and response, that's really what I focus on. How do I take science data and then respond to exploration and mission objectives, which kind of gets into the second one, based on the data that I'm seeing. So you could decide to take one or more of these based on how much computational power you have, how, like, what is the importance to your mission? So whatever you want to do. So that's how we're trying to build it. And then what are we doing now? So we are integrating more challenging decision making. You can see sometimes it's been fairly easy, like, okay, well, I think I see something awesome. So what do I do now? And so now we're trying to say, well, what if I see more than one amazing thing, and I don't have the resources to do both of the things that I want to do? So now, how do I make that decision? So that's the stuff that we're working on right now. We are trying to figure out how to do updating models on the fly, which is pretty interesting. So we're kind of using kind of a reward function for how to do that. We are conducting more field tests, and we're planning to do even more field tests in the upcoming year. And hopefully, I hope soon in the next couple of years, we'll deploy in space. That's the plan. So I just wanted to show off the work that they all did this summer. So this is Lily again, Leighton and Connor, Dr. Brett McKinney, who I've been working with for years at the University of Tulsa, and then our two new collaborators that are actually biochemists, Dr. Mohammed Fakir and his grad student Milan. And I'll leave it with the acknowledgments. I hope I have said throughout this talk how lucky I am to work with this incredible group of people. And I keep just finding more amazing people to work with. And I'm just really, really appreciative of all the work they've done. And every time I ask them to do something incredible and crazy and it doesn't make sense, they're ready to go. So, so I really appreciate that. Yeah, I'm happy to take questions. Thank you all for your attention.
Bethany, that was unbelievable.
Oh, yay.
I was nodding in agreement every slide, and then it just kept getting better and better. So
Yay.
if you have questions, please feel free to raise your hand using the raise your hand feature or post it in the meeting chat. Bethany, are you able to see the chat?
Let me look. Yes.
And I see,
Okay.
let's see, do we have any raised hands yet? Okay, so let's go. Bethany, if you wouldn't mind, do you want to take Hamid's question? The nice where it begins with nice presentation, and then we can switch over to raised hands.
I guess my question is, okay, so yeah. Given small sample size, I'll just read it for other people. Given your small sample size for a random forest, how reliable is the evaluation of your ML model? Have you done any cross-validation analysis? Also, I believe reporting results in terms of precision recall is more informative than accuracy. That's a fair point. So all of it, fair points. Yeah, so some of our models have had a much larger sample size than others, which is a fair point. So it's interesting because I think it'll make a lot of sense. If you have done any machine learning, it'll probably make sense to all of you. So if you our salt detection algorithm, so if you want to say, what is the seawater chemistry? Those are actually a slightly lower accuracy than our biosignature detection, which has a lower sample size. And so, yeah, it's one of the things that we recognize is that we need to have more analyses to do better training and also more diverse analyses. I think that the seawater chemistry analyses are incredibly diverse, or I would say that they're quite diverse. I would say that the biosignature detection algorithms that we have, they're on diverse chemistry, like in diverse seawater chemistries, but only using a couple of strains of microbes. And so I totally understand that those are trained on those specific environments. So I think that we're going to have to do a lot more work on that. In terms of cross-validation, we have done a little bit of this. So there's, of course, training and testing. We've also tried to do some independent work and try to throw something new in there and see how well it does. It's doing pretty well, but we do need to do a lot more testing on that. I'm hoping that I responded to most of those things.
Okay, let's hit, Max Coleman has his hand raised, and let's hit Max's question.
All
Max,
right.
go ahead.
My hand. Okay, Bethany, lovely presentation, thanks. Good to see you again.
You too, thanks.
quick question for you before I go to another meeting. To what extent is it going to be easy to integrate what you're doing in terms of decision making with the autonomy we already have, and which is being used on Mars at the moment for moving rovers to where they need to be in the most efficient way?
That's a great question. Yeah, so the work that I have currently proposed, hopefully funded, it sounds like it's going to be great, is actually on extensibility. So one of the things I didn't put this on my last slide, but one of the things that we're trying to work toward is how could you call upon a current NASA asset or a JAXA asset or an ESA asset for assistance? And so we're trying to think about. I am, of course, focused on the science gained from that. And so a lot of it is going to be trying to figure out easy ways to interface. So I think some of it is we're trying to use coding practices and interfaces that are common practice across NASA effectively for right now. So I think that's part of it. And then some of it is going to be security based, to be perfectly honest. So, and that's not my forte and like way outside my wheelhouse. But I do think that that's part of that conversation is that I think we as a whole, and I mean that in terms of the spaceflight community, we're going to have to start thinking about ways to grant access to those sorts of things so that those interfaces can happen more readily.
Yeah.
Hopefully that answered your question.
Absolutely. Thank you very much. Great call.
Yeah.
I've got to go now. Thanks. Bye.
Thanks. Appreciate it.
Let's get the next person with their hand raised. Penelope, you want to go ahead?
Yeah, hi, can you guys hear me?
Say something again. You sounded a little quiet.
I can
Penelope.
barely hear you, Penny.
Okay,
Yeah.
I'm gonna scream into the
Okay.
laptop. Okay. So maybe this is not a fair question to ask a geochemist, but I'm really interested in the cross correlation between image data and chemistry data. You know, eventually, I realize we're not ready to do it next week. You know, as that funnels into the decision process, because as you well know, I deal with a lot of image data and it's a pain in the ass, shall we say, in order to, you know, subject it to things like our current levels of AI capabilities. And so I'm inviting you to speculate wildly about what direction you think we might be able to go with that.
Oh, no speculation needed, actually. So, this is something that I thought of early on because very like Bethany from maybe 3 or 4 years ago was like, "Oh, this is an easy way to do it," and I was completely wrong. So I'm constantly having my ego checked here. But basically, yeah. So looking at image processing is I would say it's easy but computationally expensive to do
Yeah.
on board. And so what we're trying to do is come up with, are there lower swap ways to get the same kinds of information from imagery and then use your imagery later on, if that makes sense. So some of it is like, can you use LiDAR or can you use time of flight sensors to give you like a spatial awareness? And then so that could guide you to say, oh, I want to take an image here because this, you know, the chemistry looks cool, or maybe my spectra looks really interesting. And my time of flight sensor says like, oh, I'm close to something that might be of interest. Then I take my picture. And so then so I would actually flip it on its head from what, at least this is what Bethany thought several years ago. She was like, oh, you take a picture first and then you do all this other stuff. And I think now I would back it up and say, use all of these other ways to then say, here is the best place to take a picture. It like if you're, you know, in a longitude, for instance.
Thanks.
Yeah.
Okay, let's get Caleb. Let's get you real quick.
Okay, thank you. Bethany, fantastic. I'm just so many thoughts going around my head. Let me pin down this. This is kind of pushing things to the limit, perhaps, but I'm really fascinated with your animation of your multi-satellite mission around Enceladus. Maybe what you've done already incorporates this, but I was kind of wondering whether there's a way to sort of do a sort of meta science, meta mission design where, for example, as a satellite sees something, the decision isn't just, oh, we'll go back and look at this because it shows potential biotic origin, but the decision could be a level above that, which is actually this event or this anomalous data or this just this data will be more useful for, let's say, geochemical science than it is for a search for life. So we'll bring to bear the necessary analysis and instruments on that science question. That's part, could that be part of this sort of live, real-time decision process?
100%. And it actually makes me really happy to hear you all say things that I'm like, oh, we're on the right track, because this is another thing that we're working toward is how do you actually code in mission priorities? So if you're going to have this autonomous, like, let's say a completely autonomous mission, or give it a frame of time where like, okay, well, when you're out of contact with Earth for, I don't know, 3 days, then what can you do within that time? It has to be completely autonomous and also low risk. So we're trying to code in ways that you could think about, and I'm of course leading the science part of this. How do you take your mission objectives and then put that into a reward framework? So 100%, I'm excited. And honestly, I hope if anybody out there is from headquarters, I hope that you see this conversation and you're like, we need to start funding more stuff like that. Not just for me, but because I think that the whole community recognizes that these are the crucial components of making that work.
Thank you.
Yeah, awesome question. Yeah, and it makes me very happy to see.